We are pleased to receive Professor Martin. This is the third day, right? Third day, third day. Day three, day three.
Yeah, hi. Oh, yeah.
So now you're going to receive Professor Martin Guay
Okay.
from Queen's University. I have some story with Martin, I think in 2014 in CDC.
Yeah.
No, but I was.
Yeah, that's right. Go ahead. Yeah.
Yeah, the story is, I think you were the chair of the first time I presented a paper on extremum-seeking. It was in CDC 2014. And in that time I was using extremum-seeking with sliding modes, and then many things changed after that. But I remember this. I think Rohe was in the session as well. But after we had the pleasure of receiving Martin in UFRJ. Professor Amit is not here anymore. He gave a talk.
Oh, he was here?
Yeah.
Oh,
he was.
Oh, sorry.
And, Martin gave a talk on extremum-seeking. I think you spent some time for the Olympic Games, right?
That's right. Exactly.
And so since then, we have been working in the sense that Martin is the vice chair of the IFAC Technical Committee on Adaptive and Learning Systems, is the senior editor of TAC, and the editor-in-chief of Process of Control from IFAC. So, and today he's going to present this data-driven control of nonlinear systems using extremum-seeking.
Yeah. Okay, great. Thank you. Thank you. And really remember my time coming here in 2016. Because I remember landing early in the morning, and then Archimiro got me to the hotel.
Yeah.
And then I took the train. I went right to the basketball games. It was so much fun. Yeah. So thank you for that. That was a very, very nice visit at that time. But and I would like to thank Mario as well for selling because I don't have to talk about it. I just have to say, well, what's wrong with it, and then we're done. Okay, so that's basically what I would like to talk about today is how we transit ESC from a real-time optimization technique to essentially a control or a feedback optimizer, using what Zhangping Jiang calls it, the feedback optimization problem. And so essentially what we're trying to do is we're trying to stabilize the system to an unknown optimum. Okay, so in real-time optimization, you only need to worry about the input, and then the states do whatever they do. So you assume that the system is stable, and then you fix the input, and then you're done at the end. Okay, so what we have to do in this case is we have to compensate for the fact that the states may escape and go away from the optimum. So we want to do this. So where is that relevant is in systems that are essentially the exact same example, is that systems that are operating in unknown environments. So, and these are all examples of, for example, the effect of airflow here could be an impact. So, because they can be going fast, so there the wind could disrupt. Obviously, here is another issue. Here, the environment is essentially the terrain. And in smart grids, could be the demand, could be prices, could be anything like that. So, so these are variables that have very big impact on the dynamics, but are difficult to model. So this is where I think this would sit, is that the way you handle this now is that you use a learning technique. So if you think of Bayesian optimization, deep Gaussian networks, machine learning, where you take the system, essentially take the data that you have and make a code with it so that you can use it to predict, to control, to optimize. There's data-driven. So there are well-known drawbacks and advantages here. The main one is that it's highly unstructured. It's a black box. It works for any sort of problem that you can generate data for. So that's really, really good. Okay. Problem is it requires substantial experimentation. So in some applications, it's cheap. right? So if you have a cyber twin, it's cheap to do a lot of experiments. If you don't, then data is expensive. Meaningful data is expensive. So I come from a chemical engineering background. Data is expensive in the chemical industry. You can't just go in and repeat and repeat and repeat day after day and hoping that you could learn something. It's too expensive. There's data-driven control, which is a technique that has arisen quite a lot in the last, I would say, 5 to 10 years. But most of the techniques would rely on what we say a specific kind of model, right? So usually the data-driven type of techniques, so LQR, LQG type of techniques would rely on an LTI type formulation. Reinforcement learning is extremely powerful as well. So it's a model-free technique, but again, as in this case, it requires the exploitation, experimentation, and a data-intensive kind of approach. Okay. So there's model-free control, and this model-free control dates back to, I think, what Michel Fliess started talking about this, where you're essentially trying to minimize the impact of the model on the control. And I think what I'm talking about here is really closely related to what extremum-seeking control can do in this context. Okay, so let me just move along. So we all know the basic objectives of ESC. You start with an unknown dynamical system. So here, F is unknown, dimension of X is unknown, H is unknown, but we measure Y, and we have a degree of freedom that we can manipulate. That could be a control, could be a controller parameter. Okay. So what we want to do is really we want to find a control that gets us to the minimum or the maximum value of this measured value. So H of X star, and this X star has to correspond to the steady state value at U star. Okay, so we don't know X, so this X star is irrelevant, right? So essentially what you would get is a relationship between the input U and the steady state cost of Y. That's what we're looking for. So this is really geometrically, this is what we have. So we have our state space, steady state manifold. Essentially, we assume the system is stable, so you get to the steady state manifold, you run around the steady state manifold. Why? Well, we want to find this point here. So this has all the assumptions. You assume that this steady state manifold is locally exponentially stable. You assume that the gradient descent on this is globally exponentially stable. And then the extremum-seeking controller that we have, that the standard one will give us the standard gradient descent, right? So this is just a gradient descent. But it has to be run, for stability, it has to be run at the small enough value of the frequency. And of course, this is the result by Christic and Guay, okay? Where they showed that you combine the exponential stability of the average dynamics, so local exponential stability of the steady state manifold of this dynamics, and you can show that there's an omega star such that for every omega less than that, you get to a neighborhood of the unknown optimum. This is extremely powerful because this is a really minimum requirement on nonlinear dynamics, local exponential stability. Okay. The problem is, and that is what Mario was stressing, is that the requirement is that we have small omega. So the perturbations have to be really small so that it really does limit its applicability. Okay? It can be also, has some limited robustness to noise. Okay? But the main one is, if we want to use it for optimization in real time, it's too slow. So tons of people have worked on all kinds of formulations to try to improve the performance. And I'm listing just a few. And if you're not there, please, but I think that the main ones are based on the formulations. Okay, I think the main one from my perspective is the Lie bracket averaging technique. I'll explain why a little bit later. Then we have these estimation-based or adaptive KLS, RLS, and Kalman filter-based techniques. So we had one, and then Haring and Johansson had one in 2016 that was quite nice. And also there's all the sliding mode, stochastic, the global search techniques, and of course the ones by Zhang and Ordonez by looking at numerical optimization techniques. So you're running the real-time optimization as an optimizer would by providing infrequent updates of the gradient. Newton seeking. So this is an important one because it showed us how we could do a Newton step and how we get rid of the effect of the scaling of the Hessian, because this has an impact on how we can assign the gain. Okay? Now the last thing is, I would say, removing the time scale was for us the thing that needed to happen for this to be a bit more applicable. And so I would say with Mose and Manzi were the first one to really talk about this for a Hammerstein type of representation. And then starting in 2016, we started talking about this dual mode technique, which Mario talked about. So I'll just introduce that topic a little bit if you're not familiar. Okay? If you are, then please ask me questions if there's something you'd like to know about. So here, just for the purpose of the presentation, I'm going to assume a control-affine system. Okay? F and G are unknown, sufficiently smooth. H is also unknown, sufficiently smooth. We have the input U and the output Y, and what we are trying to do is exactly the same thing. Now, in the classical approach, essentially we're seeking the steady state optimum. So the stability of the steady state manifold needs to be implied. Okay? If we want to speed up the optimizer, we need to figure out what are the conditions where we can achieve both stability and steady state optimization. Okay? And at the end, can we minimize the impact of timescale separation? So this involves introducing some assumptions about the state behavior and the cost function. Okay? So, of course, we're going to assume the cost function has a unique critical point, okay, at x star. We're going to assume that it has relative degree 1. Okay, that's an important one. Okay, and then I'll try to relax that at the end. Okay, if I get there, depending, because I'm the last one to talk, so I can finish whenever I want. So you can nod if you agree with that. Okay, so so here, if I let LGH be the directional derivative of H in the direction of G, we can then condense these two assumptions, right? Saying that X star is the only point where LGH is 0. Okay? So in this case, the LGH of X star becomes the gradient, right? In a way, but it's not. So we add a couple more assumptions to assume that H is sort of Lyapunov function-like. That's a bit extreme. We could do a partial stability approach, but let's just, for the purpose of this, let's just look at this one. Okay, so upper bounded by class K infinity function. And we're going to assume that if we use this feedback, which is a standard damping feedback, subject to an unknown steady state U star, and we do the time derivative of H, then we get this expression. So which means that this feedback will stabilize the system. So it behaves almost like a CLF. Okay? So the thing that's interesting is that if you let these assumptions 3 and 4 be satisfied for the nonlinear system with the cost H of X, then the steady state cost L of pi U hat is such that LGH at pi U hat is the gradient of a convex function which is exactly the same optimum at U star. Okay? So then what happens is this is the gradient of a function that is not H at pi of U, but it has the same minimum. Okay? So doing that, what we can show is that this is what we call our target system. Okay, so our target system looks like this. So then we add this U hat, and this U hat is this integrator. Okay, so based on the assumptions that we just stated, this is globally asymptotically stable at the unknown X star U star. So it does the job. Okay. The reason why we add this is that we get rid of the argument of using a LaSalle invariance principle in proving this stability. Okay? All right. So we solve, so at the end, we can solve under these assumptions the combined control and optimization tasks. Okay. So of course we can't implement this. We don't know, we don't have a model. Okay? We have those basic assumptions, we don't have a model. So we have to estimate LGH. So how do we do that? Well, we can do this using a Lie bracket averaging technique. And I'll talk a little bit about a perturbation-based technique, which is just a slight variation on the original one, and the estimation-based technique, which Mario talked about. Essentially, they all come down to this estimation of LGH. Okay. So in the perturbation-based framework, it looks like this. Okay. So what I have is I have a system. This is my input. Okay. This is a high-pass filter. Okay. And V, in this case, plays a role of an estimate of dy dt. Okay. So what I'm doing here, okay, so this gives me an estimate of dy dt. So I'm correlating dy dt with sine omega t, and essentially by modulation, this gives me LGH directly. Okay? So that's the structure. I could add a low-pass filter to each of these paths if I want. Okay? All right. So that's essentially the same structure, just that we have the proportional term and the integral term. So what do we gain? Well, we gain in the perturbation case, we gain something that's really easy to tune, unlike the estimation based. So it's a lot easier to tune. But this involves the estimation of a derivative. Okay? So, but the main point here is that under these assumptions, we can have optimization. So convergence to X star and U star, okay, in a neighborhood that's inversely proportional to the frequency. And the stability will be guaranteed for every omega greater than some omega star. Okay? So it's a high frequency. So there's a time scale separation, but on the other side, to compensate for the techniques. And this is, the intuition came from Manzin Mo's paper on fast CSC. The key parameter is A over K, which is the amplitude of the dither signal divided by the gain of the LGH. Okay? Because the degree of the region of attraction grows with this size. So if you do not know where the optimum is, what you do is you pick a larger amplitude. That makes sense. Okay? And the smaller the gain, the easier that you will be able to stay within that same region. Okay, so that's easy to tune. So just to give you an idea, here's a minimum phase system. Obviously, so this is the cost that we're measuring, and we want to bring the system to the optimum of this, the minimum of this cost, which is given by this expression. Okay, so these are the tuning parameters. So it's not hard at all. Okay, this is just the order of magnitude that we have to focus on, and that's it. So this is the output. It goes to the minimum U hat. That's the U star we're trying to identify. So as a user, these are the only two graphs that I will see because I don't have X, right? So I will never see this. But you see that they all go to their steady state. Okay. Okay, so there's a lot of oscillations. Yes, that's extremum-seeking. So, but there's a more successful, I think, a more valuable contribution, and it came from the work of Shanker and Christic, who proposed these, what we call these bounded input Lie bracket approximations. And the dual mode algorithm in this context is given by this expression. Okay? So if I do the Lie bracket averaging of this term, this is minus KLGH. Not totally obvious, okay? But there is a way to approximate the trajectories of this system so that this is minus KLGH. This is minus KLGH, okay? So that means that we have the target system from a Lie algebraic perspective, okay? So the main contribution there is, I would say that what Schenker and Christic, they looked at stabilization, so they just implemented that. So of course, this will not give you the right steady state input. Okay, so it's just a light that's flickering. Yeah. Okay, so just adding this gives us the right steady state in the input, and that's it. There's not a lot of. So you see that this the averaging, and we get the result. Okay. So I mean the small lemma that I talked about, where we get the LGH being the gradient of a steady state cost function, is really helpful because we have uniform asymptotic stability of this, so which is nice. Okay, so an application of this. So this is the bounded Lie bracket. And what we've been working on is, well, we've been working with a startup company, and what they want to be able to do is to fly formations of balloons to set up networks in the stratosphere. So they fly a balloon 20 kilometers and up. And what they would like to do is to be able to station keep each of these balloons. So the station keeping problem is take longitude, latitude of interest for each of these balloons. And you say, give me a certain area that you would like to stay within. So maybe a 50-kilometer radius from the longitude, latitude. Okay? And so you have these balloons, and they're equipped with a GPS. They can measure the local velocity of the winds. They have actuation. The only actuation that they have is they can vary their altitude. Okay? So in this case, what we do is we change the altitude, and given the wind patterns, you can find trajectories in the altitude that allow you to stay within the zone. So the idea is to get within the zone and stay within the zone. Okay? So this is NOAA data looking at a specific date, okay? And we're looking at the wind variations at various altitudes. Okay, so I have 16.5, 18.9, and these are the velocity fields. Okay, so what you see is that there's quite a lot of variations at different altitudes. So you can have the balloon go from one to the next, always trying to find a better location, better direction, and go in that direction. Right? So what we did is, first of all, we generated this cyber twin, okay, which is just a proof of concept. And this is the bounded Lie bracket dual mode method, okay. What we show here is the trajectory. So this is the location that we want, okay. This is where we start, and this is where we end up, okay. So this is starting in Timmins, Ontario, which is, it's really cold right now. So, and so you see that the balloon, just using, so all it's doing is the extremum-seeking control is sending signals, changing the altitude. The altitude controller is implementing that change, and the balloon slowly moves to the point where it wants to be. Okay? And I hope this works. So we had a test not too long ago, and this is the video from the balloon. Yeah, so we tested our little rig. Yeah. So this was launched in North Bay on the 25th of November. So it's fairly new, so I don't have all the data, but I have that video because I have to wait for the company to say the okay to give that. But it's really cool. So the company was able to build the platform and get the work done so that we can fly these balloons and test these algorithms. And ESC was one of the algorithms. There's reinforcement learning is another one that we will test. And then we have some MPC-based techniques. We're just going to evaluate all of them and see which one wins at the end. So one of the things that we sort of, well, not here. I don't want to play that now. Okay, so the one thing that you notice is that the dither signal disappeared with time. Okay, and this really comes from an idea from Miroslav's group on trying to attenuate the effect of the dither signal. And the idea is that we want to be able to reduce the amplitude, okay, so that, and reduce the amplitude at a slow enough rate that we do not get rid of the asymptotic stability of the closed loop, okay? Because what we did is, in looking at those papers, is we said, okay, one thing that we know is that the extremum-seeking controller can only learn at this rate, sine squared omega t, because that's the term that multiplies the gradient, okay? So think of this as the inverse covariance in the RLS, okay? So the dynamics of the amplitude is given by this expression. This will asymptotically go to 0, okay? Or if we have exponential stability, then we use this one. So they're both the same. So what that says is that I can only learn at that rate. And based on that, I can tune the algorithm. So if I do this, so for example, in this case, I have asymptotic stability. I'm using this beta term, and this beta term comes within the high-pass filter. A is the modulation term, which goes to 0. Okay, and for the same example that we had before, we get this nice graph. So it's really good. So now we can asymptotically stabilize the system, thanks to that great, that great idea. So now it's really good. So we have a feedback controller that gives us the steady state input exactly, asymptotically. Okay. So how much time?
Oh, yeah,
Eh?
okay.
I don't want to take too much time because it's getting late. So the one thing that we can do is, so essentially by adding the integral term, that we're able to compensate for the existence of steady state, right? So what if we have a system driven by an unknown exosystem? How do we handle that? So the only way we can handle that is by creating an internal model for the system. So in this case, the problem becomes of optimizing this output, h of xw, okay, to find the minimizer, which is now a function of the exosystem, which then leads to this optimum value of y star along the path of the exosystem. And it has an optimal internal model u star. So u star is time varying in this case. Okay. So I could go to the textbook by Isidori and Burns and say, okay, that's an output regulation problem. So this is what I need to do. The problem is with extremum-seeking control is that I don't know what y star is when I start. So I don't have an error signal to minimize. Okay? By our assumptions, we know that LGH is the right signal. So what we do is we create an output regulation problem based on the measurement of LGH, which we know we can estimate very easily. So then from this point, I can generate the normal form, the normal form for the system, with an output which is now LGH. So if I knew LGH, then I could do like a post-processing regulator. We have other ones. So this is one where we're looking at the internal model as a solution of a finite dimensional system. So this is nothing but an observer of the input u, so the internal model and all its derivatives. Okay, and then this is a standard approach of doing that. Okay. Of course, we don't have LGH, so we use this. Okay. So we have, this is our signal, this is our LGH. We send it to this observer, and the first element of the Z vector is the internal model. Okay, so we have an estimate of the internal model. Okay, so I'll just give you one example. This one maybe. So a Lorentz system. So classical. Okay, so what we want to do is we want to be able to minimize this. Okay, so here the optimum will occur at x2 is equal to w1 minus 1. w1 being the output of the exosystem, which I do not have. This is the tuning, and this is what we get. Okay, so this is an internal model. So we could use this at the very least to get an estimate of the internal model without having to do the entire modeling, because this is useful for later applications. Okay. And there are all other examples. Of course, this is one of the things that we'd like to do with the balloons, because there's no structure, I can change the parameter theta, and the ESC will just recover for that. And you can see that if we change, for this simple problem, change the frequency, and this is the performance that we get in this case. So I get this internal model, which changes at every theta. Okay, so it's good. Okay, and finally, so what we'll talk about at the session on Wednesday is how we extend that to high order systems. So now we had this first order relative degree 1 assumption, and we want to remove that. So what if h is only a function of x1? Okay, but my dynamics has x1 and x2 in it. So that at the very basic, so second order system. Okay, same assumption for the steady state cost, no difference. So for the cost h of x. Okay, and the main thing is in this case, because there's no LGH, everything goes to the first non-zero term it's going to be LGLFH. So LGLFH, under the assumption that LGH is 0, is going to be equal to h x times d bracket f and g. So we assume that f and g is nowhere 0. Okay, so that LGLFH is only 0 at the critical point. Okay, and we end up with this structure. So that's the problem we solve in that paper. Okay, so the main thing is, it's a really simple generalization, is, okay, we have PI. How do we do PID of that kind of formulation? And that's it. So PID is driven by LGLFH, not LGH, because LGH is 0. So it's LGLFH, the derivative of LGLFH, and the integral of LGLFH. Okay, so this is our optimizer for the second order system, or feedback optimizer. Okay, of course we're going to assume minimum phase. And then finally, we have this result, and just want to get to the structure. Okay, so now we have second order, we need to evaluate derivatives. Okay, so we do it in two ways. First of all, we take the measurement h, and we evaluate LGLFH. So we need a signal that gives us LGLFH. Okay, then, so any observer, so any high gain observer will work in this case. Okay, and this is what we do. So what comes out here with the same demodulation idea, okay, so we'll get LGLFH. Now we need the derivative of LGLFH. Okay, so here what I do is I use a non-peaking observer to get rid of the impact of this high frequency signal that comes in from the error that the observer is making. And then I have the P, I, and D. Okay, it's exactly the same thing as what we had before. Of course, it gets a mess. So How do I do third order? I don't know. Because it'd be very, very difficult to prove. Okay? So finally, just to give you an example, this is feasible. So we have a system with a minimum phase dynamics. X2 minus X2 star is our optimum. X2 star is equal to 2. Okay? These are the signals. These are the tuning parameters. Okay? And that's the biggest worry that we had is, are we able to estimate this LGLFH and its derivative? And you can see it does a really good job. Okay? We have the estimated one is the blue, and the red one is the actual one. So it does a really good job. So overall, and this is, okay, it finds the optimum. But we're more interested in how good the estimate of LGLFH and its derivative was going to be. So I would say that at this point, we have a better handle on how we could generalize this. So we start with an amazing technique to solve real-time optimization problems. Put a few more assumptions on the states, now we're able to do feedback optimization, okay? Without any models. So any applications, we don't know what the order is, yes. So we have to make some assumptions. But we could say that at least there's a way to extend what we're doing with the first order case to the second order case. Okay? So I would say that what we have is we have a way to stabilize the system to an a priori unknown optimum. Okay? So we are generating a feedback optimizer, and we also generalize to robust output regulation designs. Okay? So this PID form gives us a way that we can extend these results a little bit further. Okay? But that remains difficult. So the higher relative degrees would be very difficult. Okay? But what we're thinking is that the Lie bracket averaging would be the way to generalize that even further. And I believe that it's possible because we want to get rid of, because the Lie bracket averaging would allow us to get rid of the high gain observer, which is really the limitation in this case. Okay? And so I don't know if I've convinced you, but I think ESC can qualify as a model-free data-driven controller design approach. And it's also a very active and fruitful area for R&D, not just on the theoretical part, but on the applications part. So I'm listing all the applications. I know there's thousands of patents with ESC. You have a few, right? Mario has a few. We have a few as well. So it does provide an extra tool to deal with complicated problems. And in relation to machine learning, I would say that the main attraction of ESC is that it's a data efficient technique. It only generates the data that's needed to solve the problem. Okay? And it provides the stability and performance guarantees. Okay? And I think I've got to thank all these people, especially those guys. And that's it. Thank you for the invitation. That was great. Thank you very much.
Thank you.